Hello, we're going to try to show you how to use a Matlab script to analyze a sound file. Here is the script I'm going to use, and the file itself is out here on my disk, and it's in Yamaha console files. See, it's going to be this B2, which turns out to be a WAV file. Let's see where it says here, Windows Media. Yeah, it's a WAV file. All right, so there's where the file is. Now the question is, how are we going to run this file, this script? Well, you could click on will run, and that would start up this script. But I'm going to assume that you are not a experienced Matlab user, so you're going to start from scratch, which means you're going to have to set up all these files that are needed by this one script right here. This script uses a lot of support files. So we're going to go out to the web and look at my website here. This is this website, which I'll show you later on. For example, it's this guy right here. Going to go out there, and we're going to look under C, which is collecting and analyzing piano data using Octo and Matlab or Audacity. And we're going to come down here at the bottom, and here's using Matlab to analyze an individual sound wave. And here's the name of the script I'm going to use, analyze a wave from file. And unfortunately, it requires all of these files here to support. And they are here. All these files. There's a lot of extra files here that I use for other scripts. I use to support other scripts. So you don't have to do all of these. But if we go back, these are the ones you need. There are about 20 of them, which is going to be kind of a pain. So what you need to do really is make a list of these things, copy these things out, and print them out on a piece of paper, and then go through and download them. Now, to do that, you're still going to have to go out here to your Windows disk and make a file to put these things. So I'm going to say new folder. I'm going to call it My Matlab Scripts. All right, then we're going to download these files into that directory. And I'm going to go here, for example, and I'm going to say, let's see, let's find one. Here's one for sure. Call input. Going to click on the download button or arrow. Down here at the bottom it says save. It's going to save as. And now I'm going to go down here and save it in that directory I just created. And I'm going to go ba-doomp like that. And it should be on there. Let's see if there it is. Okay, now you're going to have to do that, unfortunately, for about 20 of these files, the ones that are listed under this group right here. Yep, this group here. So I'm going to assume that you've gone ahead and you've done that. Now, go back here to Matlab. This is the Matlab command window. Now, you've got to tell Matlab where to look for these files. So you've got to come in here to this thing called set path. And you've got to go in here and you've got to say add a folder. Now, this is a bunch of stuff that I have already put in here because I use an awful lot of stuff. But yours won't have this. Yours will have probably well, let's see. Yeah, here we go. You'll have, starting for example right here, you'll have a bunch of these files in your path. But we're going to add a folder, and we're going to go in here to Windows. We're going to go to My Matlab Scripts. You're going to select that folder. See it is up here? Add it to the list, then you're going to say save. I'm not going to do it because I'm not going to use it, but you click on save, and that would put this directory in your path, and all those scripts that you had downloaded will be now accessible. No, I'm not going to save this. All right, so now here we are. Let's go back to the script, and let's run it by clicking on the run button. Or you could go out here and type it in, which I'll do instead. Analyze a wave from file. All right, and it comes up and it says enter the directory containing the wave. It's got a default one here, which is not what we want. So we're going to go and type in the name of that directory, which is okay, there it is. I'll keep it up the top there. So it'll be C D drive files Yamaha console files single string experiments. Now hopefully I typed that in properly. Let's see if it took it. It liked it. All right. Now it's a WAV file, so I'm going to use 2, which is the default. And the name of the file, excuse me, I'm going to take a drink of water here. The name of the file is b2, and I got to put b2.wave. So it's b2.wave. Now the script generates a list of all the variables that are in memory, and you want to take a look at those and figure out which one you just read in. And it's pretty obvious because it'll be the one that's long and it's got 2 channels. So here this is it, W wave. It's 250,000 bytes long, and it's got 2 channels because it's a stereo reading wave. Okay, so the default is Y wave, so I don't have to enter anything. I just take the default. I'm going to call this the title now, Yamaha B2, and that has a fundamental frequency around 123 hertz. We can change this in a minute. Okay, let's go out to 1500 hertz for our spectra that we're going to plot. Minus 80 dB for the decibel plots. I'll use the default here. The length of the file is about 5.8 seconds, and we'll use that. I won't cut it shorter. Down here you see that it calculated the tone center of 746 hertz. Here's the time trace. Let's see, there's a little leading tab there. I think I'm just going to take that out just because I can. Okay, trim and pad, yes I do. I'm going to say 1 for that. And I'm going to take out anything at the beginning that's less than 60% of the max value. That's that 0.6 there. And I did it. It took out that leading portion and left me with this. I don't really have to do that, but sometimes it's pretty handy. Let's listen to the wave before we go on. Now let's verify where that first partial is. All right, 122.5 we'll use. You can see it's kind of crude because we're getting into the resolution of the line spectrum, because we're using a fast Fourier transform. I may even have it. Here it is, yeah. Fast Fourier transform frequency separation. So my frequencies are separated by 0.17 hertz. In a minute I'll show you how you can get finer resolution if you want. But I'm going to use 122.5. So I'll put it in there. All right, now using that as my fundamental, I get a line spectrum. The blue are the partials. I'm plotting decibels. The red dotted are the harmonics coming from this 122.5. Excuse me. And you can see right over here, I'm right on, because I picked the value of 122.5 to do that. But as you go out in frequency here, you start to see the partial get sharp relative to the harmonic, which is the consequence of inharmonicity. And we get two peaks here. That's maybe, so there's some extra stuff going on there, which we'll talk about in a minute, maybe, if I remember to do it. Now I can copy this and then go paste it on a Word document if I want. For example, here's this Word document that I'm using. I'll just go Control V, and there it is. Now I can make it smaller or whatever. All right, now while we're here, here's the site, the website that has those scripts you're going to have to download. Here's a Facebook page that contains a lot of previous postings. And then we're not going to worry about this BoxNet folder. Here, for example, is the formula we're going to analyze for inharmonicity. It says that the frequency, the frequency for the nth partial is equal to n times the fundamental times the square root of this quantity, and n is the partial number, b is the coefficient of inharmonicity. And one of the things we're going to do, one of the things the script is going to do is find b. All right, enough of that. Let's get back to the business at hand, Matlab script, and let's press enter. Okay, here's another picture. This is showing line spectrum, and it's showing the cumulative line spectrum too, along with the harmonics. And for example, you can also save this, if you wanted to, as a JP or a JPEG image, I guess you call it, JPG file. You can save that. I do that a lot because you can take those files and paste them into YouTubes and into Facebook and other things. You can send pictures over your phone because they're JPG. All right, let's get back to the script here. Let's press enter. Here's another script, another spectrums, set of spectra. This has got the linear, the decibels, and the cumulative. You might want to paste that one. Now we'll do this Giordano plot, which is a measure of the inharmonicity. Current value is 1, which is yes, so let's go ahead and do it. 20 partials. Let's put 30 in there, and I'll tell you why in a second. I'm going to look for 30 partials. There's the fundamental frequency, and I'm going to go all the way out to 3,000 hertz. All right, it went through and found all these partials. See, here's, for example, 122. It found a peak at 122.5. Here's another harmonic down here, 2940, and it found a peak at 30.65, which means there's some inharmonicity going on, which you can tell by looking at this graph of the partials in little circles and the straight line, which is the harmonics. So it's just showing you that as the harmonics get higher in frequency, the partials start to get sharp relative to the straight line here. Not particularly useful graph. 24, it found 24, so we use 24. Now here's this Giordano calculation. See, it calculates the ratio of the nth partial's frequency divided by the harmonic, the fundamental, and that ratio should be n if it's not stiff. And if I subtract n from it, it's going to be 0. So if this was not stiff, then these circles would go along here. But because I've got stiffness and inharmonicity, these circles go up. So it's a measure of the inharmonicity. Here is a picture. Let's move this out of here a little bit. Here's a picture of the model that I showed you on that previous page is actually this equation right here, the black line. Here's the partials. So the model goes through the partials. The harmonics go in the straight line, the blue straight line. And I was able to find the value of B, which is 0.15 times 10 to the minus 3. So that's the inharmonicity coefficient. And it can be useful for comparing the inharmonicity of various waves. Okay, let's continue. Press enter. Okay, here's the combination graph. We've seen these both before. Let's do a fine grid spectrum, and let's take a look at the first fundamental there, the first partial, 122.5. If I left it at -1, I would skip this calculation. So we'll not skip it, we'll actually try it. Now this is going to be a finer grid in the frequency domain than you can get with the fast Fourier transform. And we're going to do plus or minus 5 around 122.5. I can change that to 10 if I wanted to, or anything. I'm going to put 1,000 frequency samples. So the grid is going to have a spacing of 1,000 frequencies spaced over this plus or minus 5 hertz. I can change that too. Here it did. Now because I've got a really fast computer, it came up quickly. If your computer is not so fast, it may take quite a while to do this. And if you don't have much RAM, it might actually choke. But anyway, here's the fine grid. You can see you've got a spike here, dominant one, then you got a little next door neighbor here. I'm plotting in hertz up here versus power. I'm plotting it in cents over here versus power. So this is a handy plot to have, for example, if you're looking at a pair of coincident partials. So you could look at the difference between them in cents or hertz and figure out what your ear should be telling you in terms of beating. Okay, let's continue on. Oh, here's another picture, the same thing, just a bigger picture. Let's do the spectrogram. I'm going to go out to 1500 hertz on this one. And there's a floor that you can pick that wipes out some of the nonsense on one of the dimensions. You'll see it when we get to it. I'm going to use the default of 10 to the minus 10th. And if it's over here, yeah, there it is. There's the spectrogram. That isn't a very, but here's this floor, for example, this blue stuff. But if I look at it this way, you can see some interesting stuff. Now, what's this telling us? This is interesting, I think. Here, this first partial at 122.5 starts out semi-strong, I guess, dries away. Second partial starts out strong, comes down at about half a second, drops off, comes back up, comes back down at about 3 seconds, comes back up, and here it is at the end, about 5 seconds. It's hanging in there. The third partial is over here. You can see it right there. It does some whipsy-doos too. And then you can see way out here, like the 10th partial is pretty strong. But by the time you get to 5 seconds, there's really only 2 partials left. Now you can see this blue stuff here in the floor. I can get rid of that if I raise that, this number right here. If I raise it, I can get rid of that. Whoops, let's see, get back to my picture here. All right, now let's see. Okay. Now, oh yeah, why is that? Let's take a look at something here. I should have had this up ready to look at. I apologize for having to search through this to find it because I should have had it ready. These are some strings. This is some analysis I did on a bunch of strings. Finally. Okay, here are the 3 spectrograms of the B2. This is the one I just showed you, with all the little bobbing around in the partials. Now look down here. Here's the same key, but I've muted the left string. And look how regular these things dropped off. I used the same script to generate this graph here too, that I'm using now. And here is the spectrogram of the same string, except when I've muted the right string. And you can tell these partials behave, well, they behave themselves when they drop off. There's not a lot of this horsing around up here. But so the individual strings behave nicely, but when you strike the two of them together, when you strike the full combination, you get this stuff. So that's the consequence of these two strings interacting, which I think is kind of interesting. All right, let's go back to the Matlab screen. Let's press enter to continue. And here's the autocorrelation. Now I can cursor over here to the first and strongest peak, and it's going to, down here along the bottom are the time lags in milliseconds, and I'm going to be able to calculate the frequency associated with this peak. It's 124 hertz, which is just an approximate estimate of the pitch according to the autocorrelation. Okay, now here is the autocorrelogram, which is the autocorrelation changing in time. And you see there's some interesting stuff going on here. Well, for example, if I had been smart enough, I would have gone over and looked at this peak too, because this peak happens to correspond to a frequency that's equal to the second partial. In other words, the time lag is half as much, so the frequency is double. Anyway, you can see what the autocorrelogram is doing. It's got that main peak right here, which corresponds to this peak, and it lasts throughout the whole 5 or 6 seconds. But early on, you can see there's an awful lot of activity, different peaks showing up. But then near the end of it, you start to see this other peak show up, which is indicating to me that the pitch is starting to be in competition for a lower time delay or a higher frequency, which is associated with the second harmonic. So the second harmonic is starting to show up here as a competitor to be the pitch. And that is because of the behavior of these partials. See, back in here, all these partials are horsing around, and there's no clear pitch except for this one here, which is the consequence of the spacing between the partials. But there's a lot of horsing around here. Then this thing starts to develop, which is a consequence probably of the fact that by this time out here around say 4 or 5 seconds, you only have 2 partials left, these two guys right here. And so now the estimated pitch is being influenced by just these 2 partials. And so you've got this little extra peak showing up here. All right, let's continue on. Here's a combination of 2 plots we've seen before. Here's the tone center. Look at the variation of the tone center. This is also, I think, kind of interesting. Tone center is high early on, but then again, that makes sense. Oops, did I just, oh yeah, here it is, 12? Here it is, all right. Because this is, remember the spectrogram. Early on, you've got a lot of power in these higher partials. They're out here, so it's going to make the tone center high, and there's an awful lot of variation in these partials, so this is going to be some variation in the tone center. And then near the end, around 5 seconds, you've only got these 2 partials left, and you end up with a tone center of around 300 hertz, which is consistent with the fact there's only 2 partials left. All right, here's another combination that we've seen before. You might want to paste that into your document. Who knows? Okay, that completes the discussion of using this script. You have the option now of closing the figures and going on to another one. I'm not going to close them, but I will just press enter here and keep them. And now you have the option of picking a directory here for another wave, and you can continue on with your analysis. So, hopefully you are now in a position to at least try some of these things. You're going to have to go to this website, download all these scripts, which is a pain, and you're going to have to make a directory, my Matlab scripts, put them all in there. You're going to have to go to your path and whoops, I got to stop this before I do that. Okay, you're going to have to go here and add a folder. This guy here. And once you do that, then you can execute this script and you can generate these kind of files. So thanks for listening and thanks for watching.